Welcome, everyone. Today, we are examining a critical security event that has sent shockwaves through the technology industry, the WolfSSL Crisis, tracked to CVE 2026-5194. Let's get started and understand the mechanics of this 5 billion device threat. Let's start with the what. WolfSSL is a widely adopted, open-source embedded SSL/TLS library written in the C programming language. Because it is extremely lightweight, it is the go-to cryptographic engine for environments with limited compute resources. The basics of the threat come down to its massive scale. This library secures approximately 5 billion devices globally. This isn't just web browsers. We are talking about the smart grid, industrial automation, connected home appliances, machine-to-machine communications, and even military and aviation systems. Recently, a terrifying vulnerability, designated CVE 2026-5194, was uncovered. While the National Vulnerability Database scored it a 9.3 out of 10, Red Hat's independent analysis pushed it to a perfect 10. This means it is as critical as a vulnerability can possibly get. Looking at this diagram, you can visualize the vast surface area affected by this single library. The WolfSSL footprint sits at the center, branching out into critical infrastructure, consumer tech, and enterprise environments. Every node here, from home VPNs to aviation sensors, relies on this exact C library to establish secure, trusted connections. A flaw at the root compromises the entire tree. Why exactly did this happen? At its core, authentication relies on validating digital certificates to ensure the sender is who they claim to be. The flaw in WolfSSL is a catastrophic failure of validation. The library accepts incoming certificates without properly checking if they meet the minimum cryptographic strength requirements. Specifically, it skips verifying the hash strength and the size of the cryptographic digest. Furthermore, it completely fails to check the OID, or object identifier. The OD is essentially a label that declares which signing algorithm was used to produce the signature. Because the library blindly trusts the input without cross-referencing the actual algorithm used, attackers can forge digital signatures. To the WolfSSL software, these completely fraudulent signatures appear 100% genuine and mathematically sound. This flowchart walks you through the flawed validation process. An incoming certificate hits the WolfSSL validation engine. Instead of enforcing strict bounds, the logic splits, actively skipping the hash size check and bypassing OID verification. These bypasses converge, resulting in a forged signature being explicitly trusted by the system. This leads directly to the system, allowing a highly malicious connection to proceed. How does this missing logic actually break modern security? Federal Information Processing Standards, specifically FPS 186-4 and 186-5, dictate strict mathematical minimums for hash and digest sizes to prevent cryptographic collisions. Because WolfSSL's code misses these size and OID checks, it allows digests much smaller than what FPS mandates. When you artificially reduce the size of a cryptographic digest, you destroy the mathematical security of the certificate-based authentication. What makes this particularly devastating is the breadth of algorithms impacted. This doesn't just break old cryptography, it compromises modern ECC, ECDSA, DSA, and ED25519. It even impacts ED448 and the cutting-edge post-quantum standard, MLDSA. The flaw neutralizes the mathematical strength of our most advanced cryptography. This tree diagram illustrates the algorithm impact. The root failure of bypassing FPS size standards trickles down into every major cryptographic family. It compromises classical algorithms like DSA, modern elliptic curves including ECDSA and ED25519, and, alarmingly, it even nullifies the security of post-quantum cryptography algorithms like MLDSA. The foundation of trust is broken across the board. Let's take a deep dive into the code logic to see exactly how this manifests. WolfSSL is written in C, a language that famously does not hold your hand. If a developer does not explicitly write a boundary check, the compiler will not add one for you. In a healthy library, the signature verification function would contain strict conditional checks. It would state, if the digest size is less than the FPS minimum, return an error. It would also state, if the actual object identifier does not match the claimed object identifier, return an error. Because these explicit lines of logic were completely missing, the verification function simply proceeds, blindly assuming the payload is properly sized and formatted. An attacker exploits this by intentionally sending a truncated, artificially small digest. Because the software accepts it without complaint, the attacker drastically lowers the entropy, the mathematical randomness required to calculate a cryptographic collision, successfully forging the identity. Here is the sequence of the logic flaw in action. The attacker initiates the connection, sending a certificate containing a truncated digest and a spoofed OID. Inside the WolfSSL engine, the crucial steps to check the minimum size and OID matching are simply skipped. The engine performs the cryptographic math on the weakened inputs and returns an authentication success. The attacker is now inside the system. How does a threat actor execute an attack using CVE 2026-5194? The primary attack vector is complete identity spoofing. Because the digital signature is forged, a malicious actor can impersonate highly trusted infrastructure. For instance, an attacker can set up a rogue server or intercept network traffic via a man-in-the-middle attack. When the client device attempts to connect to what it thinks is its home server, the attacker presents the forged certificate. The WolfSSL library accepts it as genuine, meaning fraudulent servers, manipulated files, and rogue connections appear completely legitimate. As security researcher Łukasz Olejnik explains, the vulnerability allows a device or application to accept a forged digital identity as genuine, forcing it to fully trust a connection it absolutely should have rejected. It grants the attacker a silent, authorized front door into the victim's network. Let's review the attacker's execution flow. The client device, perhaps a smart home appliance, initiates what it thinks is a secure connection. The attacker intercepts this and presents the forged certificate. Because WolfSSL accepts the forgery, absolute trust is established. The attacker now has a bidirectional, trusted tunnel to deliver malicious payloads down to the device or seamlessly exfiltrate sensitive data back out. Let's look at a critical, real-time use case: industrial automation and smart grids. Imagine a national electrical smart grid. It utilizes millions of machine-to-machine, or M2M, nodes like smart meters that communicate telemetry to central servers. Because these are embedded devices with low power, they utilize WolfSSL for their TLS connections. Now, an advanced persistent threat group decides to target the grid's firmware update mechanism. They write a malicious firmware payload designed to disrupt the electrical grid. To bypass the security, they sign it with a forged digital signature, exploiting the missing OID and digest size checks. The smart meters receive the payload, run it through the vulnerable WolfSSL library, and accept it as a fully authorized, legitimate update from the utility company. The attacker gains silent, widespread control over critical infrastructure without ever needing a valid encryption key. This flow directly maps the smart grid attack. The attacker writes malicious firmware and signs it using the forged certificate bypass. It is deployed to the smart grid node, which relies on WolfSSL for verification. The CVE 2026-5194 bypass allows the firmware to be accepted as valid by the hardware. This sequence results in the total compromise of the grid infrastructure, turning a software bug into a physical world crisis. Perhaps the most fascinating aspect of CVE 2026-5194 is how it was found. This vulnerability sat in a massive, widely deployed open-source project for years. It survived countless human code reviews and was completely missed by traditional automated fuzzing tools. So, who found it? The flaw was discovered and responsibly reported by Nicholas Carlini, a researcher at Anthropic. But he didn't find it manually. It was discovered by Anthropic's unreleased, next-generation AI model, known as Mythos. This represents a profound shift in cybersecurity. Traditional tools look for known bad patterns or try to crash software via brute force. Mythos, however, applied deep semantic reasoning. It read the C code, understood the cryptographic intent, and autonomously realized that the logical boundary checks for digest size and OID were simply missing from the flow. AI is now identifying the logical oversights that humans have been blind to for years. This diagram illustrates the new AI-driven discovery lifecycle. The WolfSSL source code is ingested by the Anthropic Mythos AI. Through semantic reasoning, it identifies the missing logic checks, something traditional tools failed to do. It validates the exploitability and generates a report for Anthropic researchers. This leads directly to the responsible disclosure process, allowing the vendor to issue a patch before threat actors could weaponize the finding. To wrap up, how do we defend against this? The immediate action is triage. WolfSSL has disclosed the vulnerability, and it requires instant patching across your entire infrastructure. Organizations must leverage their software bill of materials, or SBOMs, to hunt down hidden dependencies you may be using WolfSSL inside a third-party application without knowing it. For hardware manufacturers, this initiates a massive firmware lifecycle challenge, requiring over-the-air updates to millions of devices, many of which may be legacy or offline. The broader lesson here is that the era of relying solely on manual code audits is over. We must integrate advanced AI security agents directly into our continuous integration pipelines to catch these logical flaws before they ship. To master these concepts and future-proof your career, I invite learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Our final diagram maps out your remediation strategy. It starts with identifying your exposure via SBOM audits. Once identified, you must execute the patching phase, rolling out server library patches and complex OTA firmware updates. Finally, we look toward future defense, shifting left by integrating AI-driven semantic analysis directly into the development pipeline. Implement these steps, and you will be prepared for the AI-accelerated threat landscape.
To find related ebook and other material for this training course, go to quicktechie.com. Now you will see all the video courses are available here. So let's move to the ebooks. You can go here, ebooks, all AI related ebooks, like you are watching currently Mythos related training. That ebook would be uploaded under this section. You can download this ebook. PDF would be available, all 300-page PDF. So you just click on the download this entire ebook. You can download from this section. So whatever training you are currently listening, corresponding ebook would be available. We have thousands of ebooks available. Now, other than that, we have on video courses which you are watching right now. This also all AI related courses are available. Similarly, for all company related trainings are available, like Microsoft, you can find it here with their respective certification training modules. All exam simulators which would help you to get the certification preparation. Just refresh if you get this kind of error. Okay, so now you can see these are all certification preparation materials. Will also be click here to the NVIDIA certification preparation material. So you can see all NVIDIA certification preparation materials. Click on any of this and it would load the entire screen and you can launch the practice paper. So this is what you can see, that you can submit the answer. We have an audiobooks available. Okay, so for each section, and these are our alumni who can you can find out all alumni who are accessing our portal.